Hi, welcome to an adversarial introduction to TensorFlow 2.0. I'm Sigrid Kaidana, Mr. Text is present too, and today we're gonna have fun with adversarial examples. What are adversarial examples? Well, maybe you have seen this already. Let's scroll down. So this is the probably best known paper on the topic from 2015. So we take a model which classifies images like, I don't know, ResNet, Inception, whatever, and we let it classify an image. Here we have a panda, and that model, okay, it's pretty much confident that that is a panda, right? So 50%. And now we add some white noise, just a little bit of white noise to this image, right? Here you see how it looks after adding the noise. And I mean, that's it isn't visible. But what happens is the network is gonna classify this as something totally different. So here you see it with 99% confidence it thought this was a gibbon. So this is pretty much fun to play around with oneself, but this is really something that used to be a bit tedious before TensorFlow 2.0. So we're gonna see when we jump to the code how much easier it gets, or how easy it gets with TF 2.0. And just in case you're actually a Python user, then you can also see the Python code for this example on the TensorFlow website. But here now we are going to use it, do that in R. Okay, so let's go to RStudio and code this. First we're going to load the libraries. We obviously going to need TensorFlow. And also let's take a look what version I'm using. So you see it's it's 2.0, one of the nightly builds actually from last night. So, and we're gonna need keras, and also we're gonna need magic to display an image. There we go. So, and now we're gonna take a pre-trained model, otherwise we'd spend some time training our own, which would be perfectly fine, but it's gonna be a lot faster. So this will be application MobileNet v2 from keras. And we don't want to train the model, we want to modify the image, so we're gonna freeze the weights. Freeze weights. There we go. So model won't change whatever we do. And so let's go ahead and start loading the image. My image will be called seefeld.jpg, I think like this, yeah. And it's from a race from this year's Nordic Skiing World Championships in Seefeld, Austria, and let's see how it looks. So there we go. Make it a bit bigger. So okay, these are our skiers, and yeah. Now let's also need to prepare the image for the model, right? And for this we can make use of very handy new TensorFlow functions. They're not all new, but they got aggregated in some descriptive ways. For example, we have tf.io and tf.image, which are useful here. So I'm gonna first just load the file, tf.io read file from that location. And as it's a JPEG, I'm going to use tf.image to load it as a JPEG. This would be decode JPEG. So here we go. If we just execute this once, and inspect the values, we see it as RGB values between 0 and 255. And this is not what the model will want to work with. Also, it's integers. We want floats, and we also want to range from 0 to 1. For that too, we can just use tf$image. There's a convert image d type. And now if I convert this to a float 32, it will already scale this to, let's just make sure that's true. So all values are between 0 and 1 now. Okay, that's not everything, but a lot already. We also want the format to be the way the model expects it, and most of these models want a format of 224 times 224. So let's add a reshape operation. This will just be tf$resize. Wait a sec, tf$resize. It should be tf$image resize. Okay, great to have that auto completion. And we want the size of shape 224, 224. Okay, there we go. Let's again just execute this to make sure it's correct. Okay, that's that. But then to feed the model, we need to do one more thing, which is we need to add the batch dimension in front, and this will be tf$expand dims right at the front. And there we go. Let's check this. Yep. So we have the image prepared, all in those few lines. Okay, actually I did these steps here, which I noted, so I can just delete this. And now let's just get the predictions from that model. We're also going to save them. Okay, without that, of course. Nearly there. That should be it. Okay. Let's see. There's the very convenient ImageNet decode predictions, which comes with Keras. Execute that. And okay, so we see the top prediction, actually the only one which really counts here with a 50% certainty is ski. Okay, that's correct, right? Now what we want to do is we want to add some really hardly noticeable minimal noise to the image, which will make the model say something totally wrong or not say anything, whatever, but we really want to make sure it does not recognize the skiers anymore there. So what's the strategy here? Well, normally when we train a model, we want to adapt the weights and we want to reduce the loss, right? So minimize the loss for training. And here we're doing the exact opposite. We're going to maximize the loss, and we're not going to change the model, we're going to change the image. Okay, so now let's be evil and fool the network. In TF2 we have this gradient tape which records operations so we can play them back and compute the loss and the gradients, which is really super convenient. So if you did this thing in TF1, you might remember that you had to use this k gradients and construct the k function, and it was pretty complicated, and I'd surely have to just copy paste it here into the video, while this is really logical enough, so one can execute it like this. So we have this context manager, the gradient tape, and inside we do our operations, that is get our predictions and compute the loss. There's one thing which is special. So now if you were training the model instead of adapting the image, we would not need this first thing. So a gradient tape watches model variables automatically, but if we want to record operations on tensors, we need to explicitly watch them. So what we do here is tape $watch image. And now that we told the tape to watch the image, we call the model. Let's say pred model image. Here we have the predictions. Oh, I just executed it like automatically. We're gonna do all this again inside this context. But let's just add the loss computation. Our loss will be the categorical cross entropy, because we have several classes. And we're going to compare the, let's say, right prediction, which we had above. I called it, let's say, where is it? Prompts here, prompts. This will be the ground truth in a way, because this was the model in best case would predict. And our pred. Okay, here we go. Now we can really execute this block, and we can also just click on loss, inspect what it is. Okay, so here we see there's the loss. And now, oh, okay, I forgot to remove this here. We need the gradient of the loss with respect to the image. So this will be tape.gradient loss image, right? Not with respect to the weights. So let's execute this one. And what that paper by Goodfellow and colleagues showed that you don't need the complete gradient, you just need the sign of the gradient. So let's say we use signed grad tf.assign grads. Okay, there we go. Let's just click this and see how it looks. So it's all either -1 or 1. Okay. And now we're gonna construct our evil image. So what you can do, I mean, I did it before, so we don't need to do too much of that here. We can vary this epsilon, right? So this is the amount of noise, adversarial noise, we're gonna add to the image. So now our main operation will be, let's call this ADV image, will be the original image plus, so we can not subtract like normally, but add. We're gonna add the epsilon times signed grad. There we go. Epsilon should also execute that. Here's our adversarial image, and as we now added stuff or subtracted stuff, whatever, so we still need to clip it to be between 0 and 1. Let's do this. Clip by value, this is, and it should be between 0 and 1, right? And there we go. Now we still have the original image here, so let's see how distorted does this actually look to us humans. Here I left this in here because of the operations we need. So this is a tensor, then we need to convert it to R, right, and rasterize it to display it. And now we can do our image read adversarial image. Didn't I execute that one? Oops, okay. Seems like I had called it like this before. So adversarial image img. Here it is. Okay, so I mean it's in the resized format, but to us it's pretty much indistinguishable, I would say. Now the interesting thing, of course, is what does the network say. So let our model do some predictions. So this will be the ADV image here in this case, not the one I rasterized. But we need, of course, also to add the decode predictions. So I'm just ImageNet decode predictions. So suspense. Decode predictions. So let's see what's gonna happen. Okay, so we see our best prediction now is a Bayesian cap. Wow, that's pretty different. And I mean the certainty is not that high, 20%, right? And all the rest just basically totally unlikely. But this is really completely off. So yeah, that's the point. So the image is hardly distinguishable, if at all, but we get some totally different predictions. Okay, so I think this is a fun thing to play around with, and also, of course, there are more sophisticated methods to construct that image, but it's already very impressive, in my opinion, that this very straightforward, easy method works so well. So now for the TF2 topic, let me switch to the web browser and show you some blog articles also from last year already, which show more examples of this gradient tape stuff, right? So if you go here on the TensorFlow for R blog in the eager category and scroll down, basically all these here, starting from last year July, they use a gradient tape to get predictions and train a model. Okay, so that's it for today. Hope you also found it's a funny topic. I certainly like that, and see you again to some other video in the Multiverse video series.